This is question 10 on the booklet. Question 10, first of all, gives us a picture of a metal rod, and it says the current passing through it in a magnetic field, and make some definitions. Well, the definitions are fairly straightforward. F, B, I, and L in the formula F equals BIL. F is the force exerted on the rod. B is the flux density. Please don't say magnetic field strength, it's flux density. I is the current flowing through, and L is the length of wire or length of rod inside the field. The question then says what condition it is necessary for this equation to apply. Well, of course, F equals BIL applies when the current is perpendicular to the field lines. If it's not, then we have to extend the formula and say F equals BIL sine theta. But for F equals BIL, we say sine theta is 1, therefore theta is 90 degrees, so it must be perpendicular. The angle between the field lines and the wire, or the bar in this case, must be 90 degrees. Then we move on to our calculations, and it says, can you calculate the value of the flux density required to hold this bar from falling? So it's a slightly strange question. We know the downwards force is the weight, the force of gravity, so F equals mg. We don't have the mass of the bar, so that makes it more tricky, but we do have density, so we can remember that mass is volume times density, and therefore F equals mg becomes volume times density times g, or gravity, and we can put those figures in there as far as we can. Volume is area times length, or width times thickness times length. We know the width is 25 millimeters, so 25 times 10 to the negative 3 meters. So that squared gives you the area, and then times by length, which we don't know, times by density times by g. All of that together will give us F equals mg, or the force downwards, the weight downwards. That's the downwards force. That must be balanced by the upwards force, which is created by BIL, the magnetic field. So we've got downwards force of gravity over here, we've partly calculated it, balanced by the upwards force of the magnetic field, BIL. In fact, BIL equals mg. Let's try and put some figures in there. BIL equals what we've worked out before, the area times length times density times gravity. Luckily the L's cancel, so we can get rid of those straight away. So BI equals this times this times this. We've got figures in here now. It says what is the magnetic field strength or flux density, so actually we want B on its own. Divide this side by I, divide this side by I, we get area times